This is AP Chemistry Cram Study Unit 2, Molecular and Ionic Compounds and their Properties. In Unit 1, we learned the atomic structure and its properties, including periodic trend. Now we know what an atom is. Now we're going to learn how two atoms interact with each other and form all different types of bonds. So we're going to learn about ionic bonds, covalent bond, metallic bonds. We're going to learn the structure of a molecule. We're going to learn VSEPR, Lewis dot diagram, hybridization, etc. Let's get started. So I always start from with the definition. So what is a chemical bond? So a chemical bond is something that holds two atoms together. Chemical bonds hold atoms together and then to make sure that they behave as a unit. So let's say for water, which consists of two hydrogen atoms and one oxygen atom, if you have just two separate hydrogen atoms and one oxygen atoms in one single container, then they do not have the property of a water. When I say property of a water, I mean it is a liquid at room temperature. It has a melting point of 0 Celsius degree. It is transparent. It can dissolve salt and sugar, all of these properties. If you only have two hydrogen atoms and one oxygen atoms, but no bonds in between them, they do not behave as a water. We don't call them water. We just call them three separate atoms. So we need to use chemical bonds to connect these atoms together, and then these three atoms, they behave as one single unit called water. Okay, and chemical bonds is especially important when it comes to identify different physical properties of a substance. So let's say for graphite and charcoal and diamond, all of these three consist of pure carbon. So this is the picture of a diamond and a charcoal. They have very different look. Diamond, very expensive. It's transparent, it's shiny, it's blingy. On the other hand, charcoal, it's dull, it's black, it's dirty. So they have different physical forms or physical properties because of different bondings and different structures in between the carbon atoms. This is why we learn chemical bonds. And chemical bonds also play a very important role in determining the course of all the chemical reactions. So chemical reaction is basically breaking up of old bonds and formation of new bonds. So it's everything about the chemical bonds. So let's say water goes from liquid phase to the solid phase. It freezes at 0 Celsius degree. Then H2O in liquid converts into H2O in solid. This is not chemical reaction, because there is no breaking up of bonds or formation of the new bonds. So if I want to define something as a chemical reaction, there must be something involved with the formation of new bonds or breaking up the old bonds. So let's say when two hydrogen atoms, when the bond between the two hydrogen atoms break, and then the bond between the oxygen atoms also break, and then new bond between the hydrogen and oxygen forms, breaking, and then new bonds are formed, then this is a type of chemical reaction. Okay, so let's go over all types of chemical bonds that we're going to learn in this unit. We have ionic bonds, and then we have covalent bonds, and then we also have metallic bonds. Okay, and for the covalent bond, there are two types of covalent bond. One is nonpolar covalent bonds. The other one is polar covalent bonds. We're going to dive deep into all of them in this unit. So for ionic bonds, usually it forms between metal and non-metal. And for the covalent bond, it usually forms between two non-metals. For the metallic bonds, of course, it forms between the metallic cations. So it's metal and metal. And this is the periodic trend of electronegativity that we went over in Unit 1. And that we know that the trend of electronegativity is when you go from left to the right across the periodic trend, electronegativity usually increases because the effective nuclear charge increase. So the nucleus exert a greater attraction towards the shared electrons. They drag the electrons like strongly. When you go from top to the bottom, usually electronegativity decreases because the energy level or the shell increases. So the nucleus cannot apply that strong attraction toward the shared electrons. Okay, so for the ionic bonds, usually the electronegativity difference between two atoms are pretty big. So let's say when you combine sodium and chlorine, sodium has very little electronegativity of 0.9, and then chlorine has a pretty big electronegativity of 3.0. The difference is 2.1. So this is one of the factors that determines the ionic bonds. For the covalent bond, it's usually two atoms with similar electronegativity, or two atoms with electronegativity with not so much difference. So let's say if nitrogen and oxygen forms a bond, most likely it's going to be covalent bond because the difference in their electronegativity is only 0.5. But we're not going to go over the actual number or actual value of the electronegativity difference in AP chemistry. You are not asked or required to memorize any of the electronegativity. You only need to know those periodic trend. Okay, so types of chemical bonds. Here is a example questions for AP style exam. Which of the following claims about a binary compound in which the bonding is ionic is most likely to be scientifically valid? Okay, say ionic bond. Well, what are some of the characteristics of ionic bond? Usually it forms between a metal and non-metal, and then the electronegativity difference is usually large. Okay, so out of A, B, C, D, A is not correct. Both elements are metals. Well, no, not both elements are metals. That is metallic bonds. B, the atomic masses are relatively small. Okay, so atomic masses have nothing to do with the types of bonds. C, there is equal sharing of electron between the atoms of the element in the compound. Okay, so sharing of electron is about the covalent bond. We're going to learn about it later, so it's not C either. D, electronegativity difference between the elements in the compound is relatively large. Is relatively large. Yes, so D is the only answer. And next, let's talk about the ionic bond. Okay, so ionic bonds form between two atoms when there is an electron transfer between two atoms. So when electron transfer from one atom to another. And here is a diagram that shows us the transfer of an electron. So let's say atom A has 1 valence electron and atom B has 7 valence electrons. If there is an electron transfer from A to B, then atom A becomes cation, which is positively charged ion, and atom B, by receiving an electron, it becomes an anion, which is negatively charged ion. Okay, and we know that like charges repel and unlike charges attract. So cation and anion, one carries positive charge, the other one carries negative charge. They're going to attract each other. So so a strong attractive force between two opposite charges form. And these strong attraction is what we call by ionic bonds. So for example, sodium chloride, then sodium forms sodium cation, and then chlorine forms chloride anion. So cations and anions, they attract each other. Or let's say magnesium oxide, magnesium because magnesium cation, and oxygen becomes oxide anion. there is strong attraction between two opposite charges, which is ionic bond. Okay, now let's talk about ionic compounds. Okay, so these two are the common examples of ionic compounds. The left one is table salt, sodium chloride. On the right-hand side, that is calcium carbonate. Okay, so both of the ionic compounds, they are in the form of crystal and solid phase. So ionic solids has crystal lattice structure. Crystal lattice is highly ordered structure of cations and anions. Here are couples of examples of the crystal lattice structure of different ionic compounds. You guys are not required to memorize or differentiate any of these crystal lattice structure. They are not going to be tested in AP chemistry exam, but you just need to know that the ions are fixed in the position. They're fixed usually on each of the vertices of this cube structure, and cations and anions, they're not free to move. Okay, so this crystal lattice structure, so this crystal lattice structure pretty much explains or contributes to physical property of ionic compounds, such as rigidity and then brittleness. So rigid means the structure is hard, it's not soft. This is because of the strong ionic bonds. Now you can see that the ionic bonds, there is ionic bond in between every single cation. So this whole structure is very stable and it's not going to be easily compressed. Remember that you're going to imagine you're going to apply a force to compress it from top to the bottom. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like 12 ionic bonds will support it. So it's not going to be, it's very difficult to change its shape. Okay, then what about brittle? So brittle is a little bit different from rigid. Brittle actually means it's easy to break when you apply the stress. Okay, this is actually also because of the crystal lattice structure. So let's say you have this two-dimensional, here is a two-dimensional crystal lattice structure of some cation, of some ionic compounds. Let's say you're going to apply a force on the right-hand side, on the right half of the sample. Then the right half of the sample will shift downward a little bit. Okay, now the cations and anions, they're not right next to each other. Now the cations are right next to each other and anions are next to each other. And like charges repel, which means they will repel each other and eventually the ionic bonds are lost in between the left half and then the right half of this piece. So it will actually break into two pieces. Also, ionic compounds have high melting point and high boiling point. So when a substance goes from solid to liquid to gas, it actually means that the bonds between the particles are weakened and eventually broken. And ionic bonds are very strong, which means it takes a lot of energy to break it. This explains why a lot of energy is required, or high melting point, high temperature is required to break the ionic bonds in the solid phase of ionic compounds and then convert them into liquid. And ionic compounds are poor conductor of electricity in solid, while they're good conductor of electricity in liquid and aqueous state. Okay, so this might sound a little bit weird at the very beginning because how come they have like these opposite properties? Okay, all of these are due to the crystal lattice structure. So in the solid phase, the cations and anions, they are fixed in the position and they are not free to move, which means there are no freely moving ions. There are no free ions to move. So a good conductor of electricity means there are free electrons or free ions, and they are free to move around like within the substance. Then this substance is a good conductor of electricity. In ionic compounds and ionic solids, there are no freely moving ions. While ionic compounds are in the liquid or aqueous phase, the cations and anions are separate from each other. They are still loosely bonded to each other, but they can glide around each other. They are pretty much free to move. So that's why they are a good conductor in liquid and aqueous state. Okay, so molten or liquid sodium chloride is represented by the particular diagram shown above. Which of the following indicates whether sodium chloride in liquid conducts electricity and best explains why or why not? I literally just mentioned it. It conducts electricity because the cations and anions, they are free to move around. So the answer will be B. Next, the particular level diagram shown above best helps to explain which of the following properties of an ionic solid. Okay, so malleability and conductivity, they are not the properties of ionic solids. Remember, ionic compounds are good conductivity of electricity. They're good conductor of electricity only when they're in the liquid phase or the aqueous phase. So not C, not D. And A, density, B, brittleness. Okay, so it should be brittleness because now in the second diagram, someone is applying a force on top left corner and then the right bottom corner. So there is there is a shift, and now the light charges are next to each other, and then there is repulsive force in between them, so they separate into two separate layers. This is the brittleness, easy to break when applying a force. Let's talk about Coulomb's law, which pretty much explains the strength of ionic bonds. According to Coulomb's law, the amount of the force in between like charges or unlike charges is determined by this formula. F is equal to K times Q1, Q2 divided by R squared. So no matter if it's positive charge or negative charge, it carries a certain amount of charge. And then we use Q to refer to the size of the charge or the amount of the charge. So the greater the charges, the greater the attractive force or the repulsive force. And R refers to the distance between the center of the two charges. So when two charges are far away from each other, the force in between them, either attractive or repulsive, is small. And when they get close to each other, the force gets bigger. Okay, so we can apply this to the ionic solids. So let's say for sodium chloride, sodium carries positive 1 charge and chloride carries negative 1 charge. So for them, the Q1 and Q2 is like positive 1 and negative 1. Well, of course, we only dealt with the absolute value. So basically, it will be 1 times 1 divided by the radius between them, radius squared. And we're going to multiply by a constant K, but K is a constant, so it doesn't really matter when it comes to compare the ionic bonds of different ionic compounds. Okay, next, let's say magnesium oxide. So on the periodic table, you can see that magnesium and sodium, they're on the same energy level, and magnesium has two valence, and magnesium has one more effective nuclear charge, which means magnesium cations, Mg2+, will be slightly smaller than sodium cation. On the other hand, for the oxygen is on the second energy shell, while chloride is on the third energy shell. So obviously, oxygen will have a much smaller atomic radius and ionic radius than chlorine or chloride. Okay, so this will be a diagram of sodium chloride and magnesium oxide. So the radius or the distance between sodium and chloride ions will be this much, while the distance between the magnesium and oxygen will be this much, which is much smaller. Okay, so I'm going to use capital letter R to represent the distance between the nuclei of sodium and chloride. I'm going to use a small letter r to represent the distance between the nuclei of magnesium and oxygen. Then for the magnesium oxide, the charge will be 2 times 2. Okay, the charge is greater and then the distance is smaller. So which means this whole ratio will be much greater for magnesium. This is large and this is small. So magnesium oxygen ionic bonds will be much stronger than the sodium chloride ionic bond, which means magnesium oxide will have a higher melting point, and it is a better conductor of electricity, and it's more brittle and it is more rigid. Next is the covalent bond. The covalent bonds form when two atoms share electron rather than when there is a transfer of the electron. And as I stated before, there are two types of covalent bonds. One is polar, the other one is nonpolar. So nonpolar covalent bond forms when the electrons are shared equally between two atoms. And polar covalent bond forms when electrons are shared unequally between two atoms. Okay, then how do I know which in which molecule in which bonds like electrons are shared equally and in which bonds electrons are shared unequally? So we're going to take a look at the identity of the two atoms. So if it's identical atoms like chloride covalent bond, then of course this will be non-covalent bond because they're twins, they're exactly the same. So they pull the electrons with exactly the same amount of force. Then what about water molecule, H2O? So hydrogen and oxygen. Oxygen has a way bigger electronegativity based on the periodic trend that we learned in Unit 1, which means oxygen is very strong when it comes to pulling the electrons toward itself. Okay, so even though hydrogen and oxygen are sharing two electrons, but oxygen is occupying these two electrons most of the times. So hydrogen barely gets to share the electrons and oxygen gets to share the electrons most of the times. So in this case, hydrogen-oxygen bond is a polar covalent bond. Okay, and within the molecule, due to the polar covalent bond, we will have the partial negative charge and partial positive charge separated in a molecule. So the more electronegative atom will carry partial negative charge, which is represented with Greek letter sigma. So sigma minus means partial negative charge. And two hydrogens will carry partial positive charge, sigma positive. So here is a comparison between ionic bond and then two covalent bonds. In ionic bonds, there is a transfer of whole number of electrons. So no sharing of electrons between two atoms or two ions. So that's why you don't see any of the sharing or any of the bond between or any of the connection between two sides of the cations and anions. On the other hand, for the covalent bonds, they share electrons. So electrons move back and forth between two atoms. Electrons move back and forth. So that's why you see that it's a whole one single electron cloud between two atoms. And for the nonpolar covalent bonds, electrons are shared equally. So it looks symmetric. The electron cloud looks symmetric. For the polar covalent bond, the electron cloud looks much bigger on the more electronegative side of the molecule. Which of the following claims about a binary compound composed of elements with the same electronegativity is most likely to be true? Same electronegativity means two atoms pull or attract the electrons with the same force. So they're going to share electrons equally. So it is most likely nonpolar covalent bonds. So the answer was B. Next, how do we determine covalent bond length? Okay. So covalent bond length is determined by this potential energy versus internuclear distance diagram. So here is an example of hydrogen gas, H2. So two hydrogen atoms, they have to be close to each other to start forming some kind of attraction. When two hydrogen atoms are like far away, like far away from each other, they don't repel, they don't have repulsive force or attractive force in between them. They just have no interaction at all. They're just two separate atoms. In this case, because there's no interaction at all, the potential energy will be equal to 0. Okay, what if two hydrogen atoms are very close to each other? So their nuclei are almost in the same spot. Okay, so nucleus carries positive charge. So when two nuclei are too close to each other, there will be strong repulsive force in between them. Okay, so strong repulsive force means it's a very unstable state. So unstable means high potential energy. So when two hydrogen atoms gets closer to each other, then the potential energy increase abruptly. Okay, what if there are kind of separate from each other, and then there is like slight overlap of the electron cloud? Okay, then in this scenario, there will be some kind of attraction. There will be some attraction between the nucleus of, let's say, atom 1 and then the electrons of the hydrogen atom 2. And vice versa. Okay, so because there is still some attraction going on, so they're gonna pull each other closer. Okay, so at a certain point, the nuclei are close to each other, and then the attraction between the nucleus and electrons and the repulsive force between two nuclei kind of balance out. So this is the perfect point of balance. And each of the molecule have different balance point. So 74 picometer is the balance point for the hydrogen-hydrogen bond. Okay, so at this balance point, it is considered the most stable, it's the most stable state, and that's why the potential energy is the lowest. So low potential energy means it's very stable. Okay, so according to this curve, I can easily figure out the covalent bond length of hydrogen gas because this minimum point in this peak represent the covalent bond length of hydrogen-hydrogen bond. And let's try to compare different types of the covalent bond. Single, double, triple. So depending on the number of the electrons shared by two atoms, we classify them into single, double, and triple. When two atoms share 2 electrons, then this is a single bond. When they share 4 electrons, this is a double bond. And when they share 6 electrons, this is a triple bond. And and the more electrons two atoms share, it means there are more overlap of the electron cloud, and then the stronger bond lengths and the shorter the bond lengths. So from single to double to triple, the bond length actually decreases. So the carbon-carbon single bond is the longest. And then the carbon-carbon triple bond is the shortest, while the triple bond is the strongest. And the single bond is the weakest. Okay, which of the following correctly compares the strength of two carbon-carbon bonds in the molecule represented in the Lewis diagram shown above? So two carbon-to-carbon bonds. Okay, so on the left side, there is a carbon-carbon double bond. On the right side, there is a carbon-carbon single bond, and we're comparing these two bonds. Of course, double bond is stronger and shorter than the single bond. So the right answer will be A. The carbon-to-carbon bond on the left is stronger because it is a double bond. And next, electron cloud. So on the left, this is the Bohr model that we learned in Unit 1. On the right side, this is the electron cloud model. So electron cloud model is a more advanced or more modern atomic structure that we study or that we believe to be true in modern chemistry. So even though Bohr model is partially true, it is true that electrons reside on certain specific energy levels, but they don't really follow this orbital, this circular orbital strictly. So rather, they are actually very random. They move very randomly, and then they move in a very randomic path. Okay, so these dots represent the possibility of electrons to be found around the nucleus. So more color around the nucleus means it's more likely for electrons to be found within this region and then this region, and then out of this, it's not very likely to found the electrons. So when we refer to sharing of the electrons, we're actually referring to overlap of the electron cloud. Okay, and depending on the type of the shearing, we can classify the covalent bond into pi bond and sigma bonds. A covalent bond is sharing of electrons, which is basically overlap of electron clouds. And as I said, a sigma bond and pi bond. Okay, so sigma bond. So sigma bond occurs when orbitals overlap head to head. So it can be between two s orbitals. Okay, so this is two of the s orbital and s orbital, and this will be right in the center. This is the overlapping part. Okay, overlap of the electron cloud. And it can be overlap of the two p orbitals. Again, this is the overlapping part. And it can occur between s orbital and p orbital. Okay, and then we call this head-to-head overlap. And then remember that overlapping part is always on this internuclear axis. So internuclear axis is a line or is an axis that, that passes through the nuclei of the two atoms. Okay, and then the overlapping part, the overlap of the electron cloud is always on this internuclear axis. That's the features of a sigma bond. On the other hand, for the pi bond, pi bond occurs only when two p orbitals overlap and then while they're parallel to each other. So rather than head to head, it's going to be two parallel p orbitals. And this is the overlapping part. And this is the internuclear axis. So for the pi bonds, the overlap of the electron cloud is above and below the internuclear axis. It's not on the internuclear axis. So that's the difference between pi bond and sigma bond. And then pi bond and sigma bond, they combine to form single bond and double bond. So for the single bond, it's always the sigma bond. It's always one sigma bond. For the double bond, it's always one sigma bond and one pi bond. For the triple bond, it's always one sigma bond and then two pi bonds. Next is the metals. So these are some of the metals, including gold, silver, copper, zinc, etc. So metals usually they are solid, and then they are hard, and then they're also shiny. So we can use the structures of metals to explain its physical properties. So this is the structure of metals in 3 dimensions, and this is what you usually see in your textbook or on your test. So metals, and metals consist of the metallic cations and then delocalized electrons. When I say delocalized electrons, I mean electrons are free to move. Electrons are not bound to each of the metallic cations. On the other hand, the metallic cations, they are highly organized, just like the cations and anions in crystal lattice structure of ionic compounds. So it forms a lattice of metallic cations, and then it is surrounded by delocalized or free electrons. And then sometimes we call this electron sea model because it is like metallic cations submerged in water of the sea of the electrons. And electrons, just like water, they're free to move between all the cations. So again, electrons are delocalized or they're free to move. Okay, so then it's very obvious that due to the property of the delocalized electrons, the metals are good conductor of electricity, no matter they are in liquid or gas or solid phase. And metallic bonds, when we refer to metallic bonds, it's actually the attraction between the metallic cations and the delocalized electrons. Okay, so I already explained why it's a good conductor of electricity because of the freely moving electrons. And metals, okay, metals are malleable and ductile. So malleable means you can actually stretch the metals to make them a very thin sheet. Ductile means you can stretch it to form a very thin wire. So basically it means metals are stretchy to some extent. And then this is also due to the electron C model or the structure of the metals. Okay, so this is the metallic cations. They form a lattice. They're highly organized, and then in between them we have this freely moving electrons. Okay, since electrons are free to move, and then the attraction between the metallic cations and electrons are considered metallic bonds. Okay, now let's see. So let's say now I am gonna compress it. I want to compress it to a very thin layer. Okay, then these cations, the metallic cations, will glide around another metallic cations. Okay, and these electrons, because it's free to move, so it will move together. So now it's gonna fill in the space in between these two metallic cations. Okay, then what about this part? Okay, now let's say I'm gonna compress it. I'm gonna apply a force and then press it to a very thin sheet one more time. Okay, so these metallic cations, it's gonna fill in the space between these two metallic cations. And again, because electrons are free to move, so they are just gonna fill in the space between these metallic cations and anions. And that's the same for this part. So eventually, because of this freely moving electrons, so metals can be stretched into a thin sheet or very thin wire without breaking. Okay, the diagram above best illustrates which of the following phenomena associated with the solids that have metallic bonding. Obviously, it's applying the force on both sides. So it's trying. So someone is trying to like stretch it. Okay. And this is either malleable or ductile, so it's going to be B. And now let's see if the reasoning is correct, because it shows how adjacent layers of positive ions can move relative to one another while remaining in full contact with an electron C. Okay, so again, this is considered all of the space between the cations. This is considered electron C. So even though the cations are not right next to each other, because the space in between them are filled with electrons, so they do not repel each other. So it's going to be B, the malleability. Next, which of the following indicates whether the solid substance represented by the particular diagram shown above conducts electricity and explains why or why not? So positive ions, they're in this highly ordered lattice structure where electrons are just freely dispersed in between them. So which means positive ions are fixed. They're fixed in a position. They're not free to move, but the electrons are free to move. So A, it conducts electricity because it is made of positive and negative particles. Of course, it's not, such as cations and anions in ionic solids. They are not free to move, so it doesn't conduct electricity. B, it conducts electricity because electrons are free to move through the structure. Yes, B is the right answer. C, it doesn't conduct electricity because the electrons are strongly attracted to the specific positive particles. So this is not true at all. So electrons are delocalized in metals. D, it does not conduct electricity because the positive particles are not free to move. Yeah, this is true, but it doesn't mean that electrons are not free to move either. So D is not right. Next, alloy. So alloy is the mixture of different metals. So let's say, for example, when you mix silver and copper, so in most of the jewelries, it's not pure silver. It has some of a certain percent of the copper mixed in it to make sure that it's durable. So some advantage of alloy is it's harder and stronger, less malleable, and less ductile than pure metals. So they can be used for, let's say, cooking, for construction, as jewelry. So they're more durable. Okay, so even though usually alloy is a mixture of different metals, sometimes it can be the mixture of metals and non-metals, such as steel. So steel is the mixture of iron, Fe, and carbon, which is a non-metal. But 96 to 98% of steel is iron. The primary component of steel is still the primary component of alloy is still metal. So it is still considered a mixture of the metals. And for steel, when you add carbon in it, it actually increased the strength by a lot. So steel is used in construction site a lot of times. And there are two types of alloy depending on the size of the substance in a mixture. One is interstitial alloy, the other one is substitutional alloy. I'm going to talk about substitutional alloy first. So brass or bronze, they are usually the substitutional alloy. So zinc and copper, they have about the same size. So when you mix a little bit of zinc in copper, the zinc will just replace the copper cations because of the similar size. So it just replaces the copper. It just takes the place of the copper. So it's substitutional alloy. On the other hand, let's say in steel, the carbon is so much smaller compared to iron. So when in the lattice structure of the iron cations, there is tiny space in between the ions because they are not square, they are not cube. They're like round, they're spherical. And carbon just fills in this space in between them because of the small size. And this actually blocks the metallic bonds, or it actually blocks the iron it actually blocks the iron cations from moving around each other, submerged in this electron sea, which increase the rigidity. Which of the following particular level diagrams best represent an interstitial alloy? Interstitial means one substance of the mixture has large size. The other one has a small size. So the smaller one just fits in the empty space in between the big the big cations. So this is going to be A. Next is the Lewis dot diagram. So we are going to learn Lewis dot diagram and VSEPR all together to determine the structure or three-dimensional shape of a molecule. So this is especially important in unit Unit 2. In Unit 3, we're going to utilize what we learned in Unit 2 to go further on intermolecular force. So you need to have a very good understanding on this topic. So what I mean by the Lewis dot diagram is it is a diagram that shows how atoms are bonded to each other within a molecule. Is it a single bond? Is it a double bond? Let's say for carbon dioxide, CO2, what is the order? Is it carbon, oxygen, oxygen, or oxygen, carbon, oxygen? Okay, so we deal with all of this in Lewis dot diagram. It shows the atomic arrangement. It shows the arrangement of the atoms within a molecule. And to draw an appropriate Lewis dot diagram, we have to follow couples of rules. So let's take a look at the first two. One is the number of the valence electrons. So let's say in oxygen gas, O2, so each of the oxygen has only 6 valence electrons, which means 2 of the oxygen has 2 times 6, which is 12 valence electrons in total. So when you draw the Lewis-Dot diagram of oxygen, you cannot have more than 12 valence electrons. This is the most important thing. This is the rule of thumb. The second is each of the atom within the molecule has to achieve the full octet state. So full octet state means 8 valence electrons or 2 valence electrons for hydrogen and helium, because octet state is considered the noble gas state or the most preferred state. Okay, so how I do it is actually very simple. So for oxygen 2, I know that its chemical formula is O2. Okay, to make sure that each of the oxygen achieve the full octet state, then each of the oxygen should be able to have 2 times 8, 16 valence electrons in total. But actually, I am given only 12 valence electrons, which means now this oxygen gas structure is 4 electrons short. This actually means they are sharing 4 electrons in this oxygen molecule. So it will be oxygen atom and sharing 1, 2, 3, 4 electrons. Okay, then what about the lone pair electrons of the oxygen? Well, each of the oxygen has 6 valence electrons. So 6 minus the number of electrons shared, which is 4, that will be 2. For each of the oxygen to achieve full octet state, they have to eventually get to have 8 valence electrons. So 8 minus the number of the bonding pair electron, 4, which is equal to 4. This means the oxygen has 4 lone pair electrons, and this is a symmetric structure, so the oxygen on the left side also carries 4 lone pair electrons. Okay, now let's check if this is the correct Lewis-Dot diagram. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 valence electrons in total. Okay, correct. And then next, the octet rule. Okay, so for the oxygen on the right, it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. For the oxygen on the left, it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. It's cleared. So this is the most appropriate Lewis-Dot diagram for oxygen gas O2. For 4 electrons shared, I can use double bonds to represent it. So oxygen double bond, and then each oxygen carries 4 lone pair electrons. Okay, so next we can try to draw the Lewis-Dot diagram of nitrogen using exactly the same method. So let's say nitrogen N2. Okay, so each of the nitrogen carries 5 valence electrons, which means 2 nitrogen carries 5 times 2, 10 valence electrons. And to make sure that all the nitrogens achieve the full octet state, then it's 2 times 8, which is equal to 16. Okay, so we want to have 16 electrons in total, but we have only 10, which means I am gonna share 6 electrons. So 2 nitrogen atoms share 6 electrons. So nitrogen, 1, 2, 3, 4, 5, 6. Okay, then how many lone pair electrons does each of the nitrogen have? Well, 8 minus 6 is equal to 2, which means each of the nitrogen has 2 lone pair electrons. And now let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 valence electrons, and each of the nitrogen carries 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So it fulfills the octet rule. Okay, so that's it. So this is the nitrogen triple bond and the nitrogen gas Lewis-Dot diagram. Okay, and next is formal charge. So most of the times we are able to draw the appropriate Lewis-Dot diagram based on the first 2 rules, but sometimes we are able to draw multiple possible Lewis-Dot diagrams, and then we will have to take a look at the formal charge. Okay, so formal charge, how we calculate it is the number of the valence electrons minus the number of the lone pair electron minus the number of the bonding pair electron divided by 2. Okay, and here's an example of Here's an example of phosphate, PO43 minus. Okay, so there are two possible Lewis-dot diagram. One is phosphorus in the center, and then it's bonded to 4 oxygen by 4 of the single bonds. So it's 4 phosphorus oxygen single bond. Each of the oxygen carries 6 valence electrons, 6 lone pair electrons. And then the second will be phosphorus in the center, and then it's bonded to 1 oxygen by a double bond, and then it's bonded to 3 other oxygen by single bonds. Okay, now let's try to see, okay, and then both of the Lewis-dot diagram fulfill the first two rules. Okay, and now let's try to calculate the formal charge for each of the atoms. Okay, so for this Lewis-dot diagram, the phosphorus has number of the valence electrons is 5, okay, minus number of the lone pair electron is 0, number of the bonding pair electron is 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2, that is equal to 5 minus 4, which is 5 minus 4, which is equal to 1. So the phosphorus carries positive 1 charge. What about the oxygen around it? These 4 oxygen, they have exactly the same structure. They're all symmetric, so I just need to do math one time. So the number of the valence electron is 6. 6 minus number of the lone pair electron is 6. And then the number of the bonding pair electron is 2. So 6 minus 6 minus 1, that is negative 1. So negative 1, negative 1, negative 1, negative 1. So in total, when you add them up, you will get the charge of this polyatomic ion, which is negative 3. Okay, what about this Lewis-dot diagram? So again, I'm going to start from phosphorus. Phosphorus has 5 minus lone pair electron 0 minus the bonding pair electron 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 over 2, which is 0. Okay, and the oxygen, these 3 oxygen have symmetric structure. So 6 minus 6 minus 2 over 2, that is negative 1. So negative 1. And then this oxygen with double bonds has formal charge of 6 minus 4 minus 4 over 2, which is equal to 0. Okay, so now let's try to compare these two Lewis-dot diagram. Okay, so 1, 2, 3, these 3 oxygens surrounding phosphorus, they carry exactly the same formal charge, so we don't even have to consider them. We only need to take a look at the phosphorus, the central atom, and then the oxygen on top of it. Okay, so on the left Lewis-dot diagram, phosphorus carries positive 1 charge and oxygen carries negative 1 charge. On the right, both carries charge of 0. So for formal charge, when this number is equal to 0, this is the best. This is the most appropriate one. So compared to 1 or negative 1 or even 2 or negative 2, 0 are considered the best, the most stable. So the Lewis-dot diagram on the right, this is the most appropriate of structure Lewis-dot diagram of the phosphate. Okay, so this is one case of the formal charge in which formal charge of 0 is always preferred. Okay, so there is a second scenario in which you don't have a formal charge of 0. On the other hand, you have a formal charge of 1 and negative 1. So thiocyanide, SCN minus, there are 2 possible Lewis-dot diagram as well. So one is sulfur carbon single bond, and then the carbon nitrogen triple bond. And 1, 2, 3, 4, 5, 6, and 1, 2. The other one is sulfur carbon double bond, and then the carbon nitrogen double bond. 1, 2, 3, 4. 1, 2, 3, 4. Again, let's try to calculate the formal charge of each of the atom in each of the Lewis-dot diagram. I'm going to start from the left one. So the sulfur has the formal charge of 6 minus the valence electron 6 minus number of the lone pair electrons 6 minus the number of the bonding pair electrons divided by 2, 2 over 2. So 6 minus 1, that is negative 1. And the carbon, that is number of the valence electron 4 minus number of the lone pair electron 0, number of the bonding pair electron over 2, so it is equal to 0. The nitrogen has a valence electron of 5, lone pair electron of 2, bonding pair electron 6 over 2, so that is equal to 0. So it's negative 1, 0, 0 for this one. And for this one, again, I'm going to start from sulfur. Sulfur carries 6 minus number of the lone pair electrons 4 minus number of the bonding pair electrons 4 over 2, which is 0. The carbon has 4 minus 0 minus 8 over 2, which is 0. The nitrogen has number of the valence electron 5 minus number of the lone pair electron 4 minus number of the bonding pair electron divided by 2. So 5 minus 4 minus 2, which is negative 1. Okay, so when we compare these two electrons, these two Lewis dot diagram, both of them carries 2 0 formal charge and 1 negative 1 formal charge. The only difference is in the left one, the sulfur carries the negative 1 formal charge. On the right one, the nitrogen carries the negative 1 formal charge. Okay, so we cannot minimize the formal charge anymore. Then we need to pay attention to these two atoms, which carries a non-zero formal charge or negative 1 formal charge. Okay, so sulfur and nitrogen, which one is more likely to carry a formal charge of negative 1? So a more electronegative atom tends to carry a more negative formal charge. And on the periodic table, when we compare the sulfur and nitrogen, so nitrogen is actually the third most electronegative element in the whole periodic table. So nitrogen is more electronegative than sulfur, which means nitrogen is more likely to carry that extra negative charge than sulfur. So nitrogen carrying negative 1 and sulfur carrying 0 is more appropriate than nitrogen carrying 0 and sulfur carrying negative 1. So the Lewis dot diagram on the right side is a more appropriate Lewis dot diagram. Okay, which of the diagrams above best represents CH2O molecule and why? Diagram 1 and diagram 2. Okay, so it's very obvious that diagram 1 is not an appropriate one because the central atom carbon, it has only 1, 2, 3, 4, 5, 6 bonding pair electrons, so it does not even fulfill the full octet state. So if we ever calculate the formal charge of these two, the diagram 1 will have non-zero formal charge on carbon. The formal charge of the carbon will be equal to 4 minus 0 minus 6 over 2, which is equal to 1. So the diagram 2 will be more appropriate, and this is because all the atoms have a formal charge of 0. Next, carbon dioxide, CO2. Which of the Lewis diagram shown above is the more likely structure of carbon dioxide and why? Okay, so for the diagram 1, the carbon in a Saturn carries the formal charge of 4 minus 0 minus 8 over 4, which is equal to 0. And the oxygen on both sides carries formal charge of 6 minus 4 minus 4 over 2, which is equal to 0. So all of the three atoms in diagram 1 carries formal charge of 0. What about diagram 2? The central atom carbon carries 4 minus 0 minus 8 over 2, which is 0, formal charge of 0. The oxygen on the right side carries 6 minus 2 minus 6 over 2, which is 1. Okay, so positive 1. The oxygen on the left carries 6 minus 6 minus 2 over 2, which is negative 1. So obviously diagram 1 is a preferred, or it's a more appropriate Lewis dot diagram because it has smaller formal charge. All of them are 0. So diagram 1, either A or B, and because all the atoms have a formal charge of 0. So A is the right answer. Based on the formal charges, which of the following is the best Lewis electron dot diagram of H3NO? based on the former charges, which of the following is the best Lewis electron dot diagram of H3NO? Okay, so H3NO, again, we will have to calculate the former charge. So I am a little bit lazy, so I'm going to pay attention to nitrogen and oxygen specifically. So for nitrogen and oxygen, if I ever calculate the former charge, then in A, the former charge of nitrogen will be 5 minus number of the valence electron, lone pair electron 2 minus the bonding pair electron 6 over 2, which is 0. And the oxygen is 6 minus 1, 2, 3, 4. 6 minus 4 minus 4 over 2, which is 0. So obviously A is the most appropriate one because both nitrogen and oxygen have former charge of 0. I don't even have to calculate the former charge of the other 3. Next is the resonance structure. Okay, so in some of the cases, we will observe that when former charges are exactly the same, there are still a variety of the possible Lewis dot diagrams for one single molecule or for an ion. So let's say for ozone, O3. Okay, so I'm gonna start from the Lewis dot diagram by applying the first two rules. So first off, 3 oxygen means it's 3 times 6. 18 valence electrons are available. To achieve the full octet state, it is 3 times 8, 24 electrons. And 24 minus 18 is 6. It means 6 electrons are shared between 3 of the oxygen atoms. And it is impossible to share 3 electrons and 3 electrons. So it has to, because the number of the electrons shared in a covalent bond has to be multiple of 2, like 2 or 4 or 6. So 2 of the oxygen atoms share 2 electrons, while the other 2 oxygen atoms share 4 electrons. Okay, so for this oxygen to achieve the full octet state, 8 minus 4 is equal to 4, which means that it has 4 lone pair electrons. 1, 2, 3, 4. And for this oxygen, 8 minus 2 is equal to 6, so it has 6 lone pair electrons. 1, 2, 3, 4, 5, 6. For the central oxygen, it will be 8 minus 2 minus 4, which is equal to 2. So 2 lone pair electrons. So ozone basically have oxygen, oxygen single bond, oxygen, oxygen double bond. Okay, but is it possible that the oxygen, 2 oxygens on the left side carries a double bond and then the oxygen on the right side carry the single bond? Yeah, absolutely possible. So oxygen, oxygen double bond, and oxygen, oxygen single bond. This is also a possible structure of ozone. And these two have exactly the same formal charge. So it doesn't really matter which one has a lower formal charge or not. Okay. So for these type of Lewis dot diagrams, we call them resonance. So there are 2 resonance structures for the ozone molecules. Okay, and eventually, when you actually observe an ozone molecule in nature, you will actually see that two oxygen-oxygen covalent bonds are actually of the same length, which means that in nature, they don't really differentiate between a single bond and a double bond. In nature, they take this resonance hybrid structure, which is an average of these 2 resonance. So resonance hybrid. So they're going to mix one single bond and one double bond together and take an average, which is 1.5 bonds. So 3 of the oxygen, they're going to have exactly the same bond in between 2. It is like 1.5 bonds. Okay, and here is another example of resonance structure. Carbonate, CO3 2 minus. So carbon is the central atom, and then there is a carbon-oxygen double bond, and then 2 of the carbon-oxygen single bond. And again, the carbon-oxygen double bond can be between this oxygen and carbon, where it can be on this side or it can be on this side. So eventually I will be able to draw three resonance structures of carbonate. And when you draw the resonance structure, you use the double-sided arrow to connect them, which means that they can switch between each other. And again, in nature, when you have a carbonate ion, you are actually going to observe resonance hybrid structure. So each of the carbon-oxygen bond will be equal to the other two. Okay, so they are sharing two single bonds and one double bond. So each of the carbon-oxygen bond will be 4/3, 4/3 bonds. So it is represented as a solid line and a dashed line. And carbonate as a whole, it carries a charge of -2. And then the charge of the -2 is also shared in between 3 of the oxygen atoms. So eventually, each of the oxygen atoms carry -2/3 charge. Next is overfilled versus underfilled. So these are actually the exception to the full octet. Okay, so remember that the full octet, so 8 valence electrons, except for 2 valence electrons for hydrogen and helium, these are considered the most stable or the most preferred state for all the elements in the periodic table. The thing is, sometimes for some of the molecules, it's just impossible to arrange electrons in a way that they achieve the full octet state. There are just way too many electrons or way too few electrons. It's just impossible to have that. Then for these elements or for these molecules, we're going to allow for overfilled octet or underfilled octet, which means even though the number of the valence electrons is not 8, we still consider it to be as stable as octet state. So underfilled usually occur when the central atom is the group 2 or group 3 elements, and the halogens are bonded to the central atoms. So let's say for beryllium dihydride. The beryllium is group 2 and it has 2 valence electrons. So it can form only a maximum of 2 single bonds. So beryllium dihydride, beryllium having 4 valence electrons only. This is an example of underfilled octet. Beryllium, it has only 4 valence electrons. But still, it's considered the octet state, like the very stable, the most preferred state. And another example will be boron trichloride. So boron, which is a group 3 element, it has 3 valence electrons only. So when it forms a single bond with chlorine, it can form 3 bonds only. So this is the best that it can do. So even though the boron has only 6 valence electrons, it is still considered to be as stable as a full octet. Okay, then what about overfilled? The overfilled octet usually occurs when the central atom is the element in group 5, 6, 7, or 8. So let's say xenon. So xenon is a noble gas, and usually, noble gas does not really form a bond with another element, but there are some exceptions, and xenon is one of them. So let's say xenon hexafluoride, XeF6. Then xenon is in the center. It has 1, 2, 3, 4, 5, 6. Okay, and since xenon has 8 valence electrons, then it will. So overfilled octet usually occurs when the central atom is group 5, 6, 7, or 8 atoms. So let's say noble gas is xenon. Usually, noble gas does not form any of the bond with other elements, but there are some exceptions. So let's say xenon tetrafluoride. Xenon forms 4 single bonds with the halogen fluorine. Okay, and since xenon has 8 valence electrons, so now it has four electrons left. So these 4 electrons will be the lone pair electrons of the xenon. So in total, xenon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So xenon will have 12 valence electrons. So even though this is way more than 8, this is still considered the octet state or very stable state. So another example will be something like PCl5, phosphorus pentachloride, and then etc. And finally, VSEPR, valence shell electron pair repulsion. Okay, so VSEPR is extremely important in determining the three-dimensional shape of a molecule. And how it does it is by minimizing the electron-electron repulsion. Okay, so valence shell electron, which means it only occurs in between the valence electrons. And then the pair means that the electrons always have to be in pair, either the lone pair or the bonding pair. And the repulsion, okay, of course, it refers to the repulsion between the lone pair electrons and the repulsion between the bonding pair electrons, the repulsion between bonding pair and lone pair electrons. Okay, so what's really important here is you will have to know the Lewis dot diagram first, and then based on the Lewis dot diagram, you can try to figure out the three-dimensional structure according to VSEPR. So the Lewis dot diagram is the first step, and then the next step will be VSEPR. Okay, the thing is, a lot of people think or they believe that Lewis dot diagram is The thing is, a lot of people believe that Lewis dot diagram is already the molecular geometry of a molecule, which is completely wrong. So let's say for SF6, sulfur hexafluoride, if you draw a Lewis diagram, then it looks like this. So this looks like a two-dimensional structure as sulfur as the central atom, and then fluorine is surrounding it just like the slices of the pizza, and it's two-dimensional. This is not true at all. So if you try to model it in 3D, then it shows this this three-dimensional octahedral shape, and then each of the fluorine sulfur fluorine bond is 90° rather than 60°. So Lewis dot diagram does not tell us anything about the three-dimensional shape. So we always use VSEPR to determine the three-dimensional shape. When we refer to molecular geometry, it is exactly what we mean by the three-dimensional shape. Again, Lewis diagram only tells us about the arrangement of atoms. Okay, so we are going to take a look at 5 different categories, and we're going to start from the electron pair number of 2. So usually we write them as MX2, which means the central atom M is surrounded or bonded by 2 electron pairs. And when I say electron pair, it refers to both lone pair and the bonding pair electrons. Okay, so for example, the most typical example of MX2 will be carbon dioxide, CO2. Okay, so I will start from the Lewis structure of carbon dioxide. It's carbon-oxygen double bond, carbon-oxygen double bond, and then 4 lone pair electrons on each of the oxygen. Okay, so around this central atom of carbon, I have only 2 electron pair. Well, there is no lone pair, and then the bonding pair is 2 only. So single bond, double bond, triple bond, all of these are considered one bonding pair. Okay, so these 2 electron pair, because electron and they repel each other because light charges repel. So they are trying to be far away from each other as much as possible. So they will be on the opposite side. They will be exactly 180° away from each other. So this contributes to the linear molecular geometry or linear shape. Okay, and then when we call this electron domain geometry when we consider both lone pair and bonding pair. And then when we consider the bonding pair only, we call it molecular geometry. Later, you will know what that exactly means. Okay, and next, MX3. This is when the central atom has 3 electron pair around it. Okay, so let's say BCl3, boron trichloride. Again, I'm going to start from the Lewis dot diagram. So boron, chlorine, single bond. Okay. Okay, again, it has only 3 electron pair, 1, 2, 3, with no lone pair electron. And then if you want these 3 electron pair to be furthest away from each other as much as possible, then the structure they form will be this trigonal planar shape. So on this plane, they are like 120, 120, 120 away from each other. This minimizes the electron pair repulsion between the electron pair. Okay, now it comes something tricky. What if one of this bonding pair is a lone pair instead? So let's say for ozone. So oxygen, oxygen single bond, oxygen, oxygen double bond, and then the central oxygen also has lone pair electrons. Okay, so the central oxygen has 1, 2, 3. 3 electron pair. Okay, so to minimize the electron repulsion, they are 120-degree away from each other. Okay, so it has the trigonal planar as the electron domain geometry. For electron domain geometry, again, we are taking account the lone pair electron as well. Okay, but when we actually name the structure of the ozone, we call it bent rather than the trigonal planar, because when we consider the structure or the molecular geometry, we don't count the lone pair electron. We only count the bonding pair, or we only count the atoms. So for the molecular geometry, we only consider these parts. So that's why we call it bent. Next, it will be MX4. Okay, so MX4 is actually one of the most common molecular geometry that we see in AP chemistry test. And one of the most common example, the most known example will be CH4, the methane. So carbon in the center, and then with 4 carbon hydrogen single bonds. Okay, so this is the Lewis dot diagram of methane. And obviously the carbon, the central atom, has 1, 2, 3, 4 electron pair. Okay, so when 4 electron pairs are furthest away from each other in 3-dimensional structure, they actually form this weird like tripod kind of shape. So just like the tripod. And then this is a tripod, and then you have another stick that's pointing upward, let's say to put a camera on. So this is exactly the same shape as the tetrahedral structure. So each of the bonds are the 109.5 degree from each other, and they're perfectly symmetric. What I mean by that is when you rotate it by 109.5 degree, so this part is pointing upward, then it looks exactly the same as this structure. Next is when one of the one of the 4 bond pair. Next, when one of the 4 bonding pair electrons is replaced by the lone pair electron, then it's going to form this trigonal pyramidal shape. Okay, because you have only the tripod legs, and then not the supporting stick anymore. So 1, 2, 3, and it is like a pyramid. but the base will be a triangle. So that's why we call it trigonal pyramidal. And the most common example will be NH3 ammonia. So nitrogen, hydrogen, hydrogen, there are 3 nitrogen hydrogen single bonds, and then the nitrogen also has the lone pair electrons. It has 1, 2, 3, 4 electron pair, including the lone pair. So it has the tetrahedral electron domain geometry again. But when we name the structure of the ammonia, we don't really take account the lone pair electron. We only consider the tripod. So we call it trigonal pyramidal. Okay, what if two of the bonding pair are replaced by the lone pair electrons? Then it forms the structure like water. So H2O. Okay, so oxygen has 2 single bonds. It also has 2 lone pairs of the electrons. So in total, the central atom oxygen has 1, 2, 3, 4 electron pairs. So again, its electron domain geometry is tetrahedral, but when we actually refer to the 3-dimensional shape or the geometry of the water, we're only talking about the bond pair, the bonding pair. So it has the bent shape. Next will be MX5. The center atom has 5 of the electron pairs, PCl5, phosphorus pentachloride. Okay, so this is interesting structure. So with center atom and then with 5 electron pairs surrounding it, 2 of the electron pair will go up and down. So they're in one straight line, they're in the vertical line, and then the other 3 are 120 degree away from each other, and they are on this horizontal plane perpendicular to this vertical line. So this is the horizontal surface, and then right in the center we have the phosphorus, and then 1 chlorine, and then 2 chlorine, and then the 3rd chlorine, and then up and down 2 more chlorine. Okay, so these 3 bonds are 120 degree away from each other, and these two bonds, they are 90 degree away from each other, and we call this trigonal bipyramidal because it has the base of a triangle, and then it looks like a pyramidal. But there are 2 pyramidal. One is up and one is down. So we call it trigonal bipyramidal. What if one of these 5 bonding pair is replaced by a lone pair electron? Okay, then it's gonna form that. Then one of these 3 bond pair will be replaced by the lone pair electron. Okay, and then you will have the shape of the seesaw. Okay, next, what if 2 of these 5 bond pair are replaced by lone pair? Then they are gonna form this T shape. Again, up and down, X, X, and on this horizontal surface, it's going to be electron pair, and then okay, so eventually it's going to be T-shaped. What if 3 of these 5 bond pairs are replaced by the lone pair electrons? Then it's going to form this linear shape. So such as triiodide, I3 minus. 1, 2, 3. These three electron pairs on one single surface, they're all lone pair electrons. Then when it comes to molecular geometry, we only consider the bond pair, these two, which are opposite to each other, so it has the linear shape. The very last one is MX6. When the center atom is surrounded by 6 electron pairs. This is actually kind of rare. So SF6 is one of the only examples. And then it has, and this means that the center atom will have two electron pairs on left and right, on front and back, up and down. So all of these electron pairs are 90 degrees away from each other. And then that's why we call it octahedral. If one of this bond pair is replaced by a lone pair, then we have this square pyramidal shape. And if two of the electron pairs are replaced by lone pair electrons, then they have the square planar shape. You will have to memorize the name of all of the molecular geometry. Okay, so now here is a review of or comparison between the Lewis diagram, electron domain geometry, and molecular geometry. So always remember that when we refer to the three-dimensional shape or just shape or structure of a molecule, we're always referring to the molecular geometry. Okay, so let's say, for example, water, H2O, its Lewis dot diagram will be hydrogen, oxygen, single bond, oxygen, hydrogen, single bond, and then 4 lone pair electrons on the oxygen. So for the Lewis dot diagram, it doesn't really matter how you draw it. You can draw it as a linear structure, you can draw it as a band structure. Both are considered correct in Lewis diagram because the Lewis diagram only cares about the atom arrangement. So how is hydrogen bonding to oxygen? Is it a single bond or double bond? Does the oxygen carries the lone pair electrons? Is it hydrogen, hydrogen, oxygen, or hydrogen, oxygen, hydrogen? These are solved in Lewis diagram. And then based on the Lewis diagram, you are going to draw the electron domain geometry, which minimizes the electron-electron repulsion in three-dimensional shape. So including the lone pair electron, the oxygen is surrounded by 1, 2, 3, 4. So its electron domain geometry is tetrahedral. So it has oxygen and so oxygen, hydrogen, and then lone pair electrons and lone pair electrons, tetrahedral. And when it comes to molecular geometry, I only consider the bonding pair or the atoms. So only these parts are considered. Then it will be the bent shape or the bent molecular geometry. Okay, next, based on the Lewis diagram for NH3 shown above, the H and H bond angle is closest to which of the following? So NH3. So N, nitrogen, is the central atom, and then it has 1, 2, 3, 4 electron pair, including the lone pair. So its electron domain geometry will be tetrahedral, nitrogen, okay, up, and then the tripod. Okay, so hydrogen, 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 lone pair electrons. Okay, and the bond angle of tetrahedral is 109.5 degrees, so the answer is C. Okay, next, let's try to compare polar versus nonpolar molecule. So now we know, because we learned the VSEPR, we know the three-dimensional structure of a molecule or the shape of a molecule. And based on this three-dimensional shape, we can determine if a molecule is polar or not polar. So there are two criteria that we take a look at. The first one is molecular geometry, the three-dimensional shape, and then the second one will be the individual bonds. Okay, so for molecular geometry, if it has asymmetric molecular geometry, then it is already polar molecule. So let's say, for example, T-shaped. If a molecule has T-shaped, So let's say the center atom is M, and then it has other atoms attached to it up and down, and then one more, and then on the left side it has the lone pair electron. So this is the seesaw structure. Okay, so this is already asymmetric in 3D, in 3D. Then I don't even have to pay attention to the bonds. This is just a polar molecule, obviously. This is polar, obviously. Or let's say bent, MX, okay. As for the bent, the symmetric, as for the band structure, this is asymmetric already, so I don't even have to consider what type of bonds it is. This will be just polar bonds. Okay, so what if it is a symmetric structure such as tetrahedral? Then I need to take a look at all of the bonds. So for example, I have a structure of CCl2H2. Okay, so it has the tetrahedral shape, but two of the bonds will be carbon-chlorine bonds, and two of the bonds will be carbon-hydrogen bonds. And carbon-chlorine bond is polar, and carbon-hydrogen bond is nonpolar. And these four bonds do not cancel out each other. They are not balanced. So this will be polar for sure. And let's say boron dihydride and boron dihydride and chloride. So boron surrounded by one chlorine and then two hydrogen. So it has this perfectly symmetric 120, 120, 120 trigonal planar structure. But because the bonds are not exactly the same, so this is still a non-symmetric, asymmetric structure, and this will be considered polar. Next. Which of the following Lewis dot diagram represent a molecule that is polar? Okay, so ABF3, so it has the central atom boron has 1, 2, 3, three electron pair. So boron, fluorine, fluorine, fluorine. It's perfectly symmetric, trigonal planar, and then each of the bond is exactly the same, so it is perfectly symmetric. This is nonpolar. And B, carbon dioxide. The central carbon has 1, 2, 2 electron pair. So it's gonna form that linear structure, and each of the bonds are the same, so it is going to be nonpolar as well. And then the next, it will be okay, so this is the example that I made, CCl2H2. So the structure, the three-dimensional geometry itself is symmetric, but because four of the bonds are not exactly the same, so it is polar. And what about D, nitrogen? Nitrogen gas. Okay, so it's nitrogen triple bonds, and then this is a linear structure, and then two atoms are exactly the same. It's even a nonpolar covalent bond. It's perfectly balanced, perfectly symmetric, so it's nonpolar, obviously. Okay, so what is hybridization? So hybridization is the mixture or fusion of orbitals of different energy subshells to form new orbitals with the same energy level. Okay, so what I mean by that is, let's say s orbital and p orbital, they have different energy levels. This is 2s and this is 2p, and when they combine together, they're going to form this, let's say sp3 orbital, and then their energy level will be in between s and p orbital. So this is what I mean by hybridization. But you guys are not required to know why it forms or about the exact energy levels of the newly formed sp3 orbitals. You will only be tested on the types of the hybridization. So when the number of the electron pair, so when I say electron pair, it includes both the lone pair and then the bonding pair. When number of the electron pair is equal to 2, then it is sp hybridization. When it's 3 electron pairs, then it's sp2 hybridization. When number of the electron pairs around the central atom is 4, then it forms sp3 hybridization. This is the only thing that you need to know for AP chemistry exam. Okay, so let's try to do this FRQ question. Answer the following questions about nitrogen gas and about the hydrazine. In the box below, draw the complete Lewis electron dot diagram of nitrogen, N2. Okay, again, 2 nitrogen atoms means 2 times 5 in total, so 10 valence electrons. That's what we are given. To achieve the full octet state, 2 times 18, we need 16 electrons for we need 16 electrons. So we are 6 electrons short, which means 6 electrons are shared within this nitrogen gas molecular structure. Okay, so it will be nitrogen, 1, 2, 3, 1, 2, 3, and each of the nitrogen will have A minus 6, which is equal to 2 lone pair electrons. Okay, so you can either draw this or you can draw nitrogen triple bond nitrogen with 2 lone pair electrons. B, based on the Lewis electron dot diagram that you drew, is the nitrogen molecule polar? No, it is nonpolar. Explain, because it is a linear shape with non-polar covalent bonds, and it is perfectly symmetric. Next, the following graph shows the potential energy of the 2 nitrogen atoms versus distance between their nuclei. On the graph, indicate the distance that corresponds to the bond lengths of nitrogen molecules by placing an X on the horizontal axis. Okay, so for these type of questions, I told you that you always look for that the peak of this potential graph, which is the lowest potential energy. Okay, so this the distance corresponding to this peak will be the bond length for the nitrogen bond. On the graph, which shows the potential energy curves of 2 nitrogen atoms, carefully sketch the curve that corresponds to the potential energy of 2 oxygen atoms versus the distance between their nuclei. Okay, so for the nitrogen, yes, so in between, within the nitrogen molecule, nitrogen forms nitrogen triple bonds, while oxygen forms oxygen double bonds. And then we know that triple bond is shorter and stronger than the double bonds. Okay, which means the potential energy for the oxygen will be higher because it's not as stable, or it's not as strong as the triple bond of the nitrogen. And also it is going to be a little bit longer than the nitrogen triple bond. So the peak of this oxygen bonds will be higher and towards the right side of the peak of the nitrogen bonds. So this is how the oxygen bonds look. Next, the Lewis electron dot diagram of the hydrazine is shown below. Based on the Lewis electron dot diagram of nitrogen and hydrazine, compare the length of the nitrogen to nitrogen bond in nitrogen with the length of the nitrogen to nitrogen bond in the hydrazine. Okay, so again, nitrogen triple bond in N2, and then nitrogen single bond in hydrazine. And obviously the triple bond is stronger and shorter than the single bond. So nitrogen to nitrogen bond in N2 is shorter. And next, compare the strengths. Okay, then it is stronger. And the last one, identify the hybridization of nitrogen atoms in hydrazine. In hydrazine, the nitrogen atom has 1, 2, 3, 4 electron pair, so it has sp3 hybridization. This is it for Unit 2.